We're going to do a comprehensive deep dive on Microsoft Fabric. We're going to cover the architecture, design decisions, trade-offs, and the production patterns you should follow when implementing Microsoft Fabric-based solutions. So let's get started. So Microsoft Fabric is a unified SaaS analytics platform that brings together multiple data and analytics capabilities into a single integrated environment. Now, what does that mean? Traditionally, when you're building an analytics solution, you're combining together multiple separate services. You have one service for data integration, one for data warehouse, maybe one for separate data lake, one for BI tool, and one service for real-time analytics. Each of these have their own billing model, its own security model, and their own governance approach. However, now Fabric changes the model completely. So instead of stitching together all these separate services, Fabric provides an end-to-end platform built on a unified foundation. It combines the capabilities that you might recognize from Power BI, Azure Synapse, Azure Data Factory, and many other services into a cohesive experience designed for the modern big data environment. So the key insight here is that Fabric represents Microsoft's strategic vision for analytics, and that vision is built on top of four pillars: unified storage, unified compute, unified governance, and unified experience across all data workloads. When I say unified storage, I mean one data lake for everything. When I say unified compute, one capacity pool that all your workloads draw from. Unified governance means one set of security policies that could be applied everywhere. And unified experience means you're working in one interface, not jumping between different tools. This architectural approach reduces the complexity you typically see in analytics platforms, and we'll explore exactly how that works throughout this deep dive. Now let's look at the major components that make up the Fabric platform. At the top level, Microsoft Fabric contains three main areas: Data Factory, Synapse, and Data Activator. Under Data Factory, you get pipelines and data flows. These are your data integration and transformation tools. Pipelines handle orchestration and movement of data, while data flows provide that low-code transformation experiences using Power Query. Synapse in Fabric is not exactly the same as Azure Synapse Analytics that you might be familiar with. In Fabric, Synapse encompasses four key workloads. First, data engineering, which gives you Spark-based processing with notebooks and jobs. Second, data warehouse, which provides a SQL-based warehouse capability. Third, data science for your machine learning and AI workloads. And fourth, real-time intelligence, which handles streaming analytics and event-driven scenarios. Then you have Data Activator, which enables event-driven actions. This lets you set up automatic responses when certain conditions are met in your data. Each of these components share the same underlying storage layer, which we call OneLake, and they all draw from the same compute capacity pool. This shared foundation is what makes the integration seamless compared to traditional architectures where you would constantly move data between separate systems. So let's start with what problem exactly is Microsoft Fabric platform aims to solve. Traditional analytics architectures require multiple separate services. You need data integration tools to move data around. You need a data warehouse for structured analytics. You need a data lake for flexible storage. And you need a BI platform for visualization. Now, on top of all of this, you also need real-time analytics for streaming scenarios. And then you also need machine learning platforms for the AI workloads. This whole fragmentation creates some significant challenges in production systems. First, data gets copied between different systems constantly. You're ingesting into your data lake, then you're copying into your warehouse, then maybe extracting for your ML platform. Each copy introduces latency and potential inconsistency and so storage costs. Second, there is inconsistency in security models. Each service has its own way of handling authentication, authorization, and data protection. Trying to maintain consistent security policies across all of them becomes an operational burden. Number three, the governance gets complex. How do you track data lineage when data is flowing through 5 different systems? How do you apply sensitivity labels consistently? And then on top of that, how do you audit across all these different platforms? Number four is then you get the multiple billing models. One service charges by the hour, another charges by the query, another by storage, and then another by transaction. Understanding your total cost becomes very difficult, and optimizing across all of them becomes pretty impossible. And finally, the integration complexity. You have constantly building connectors between these systems to better integrate them, and then you have to handle authentication between them, manage the version compatibility, and dealing with the operational overhead of maintaining all of these moving parts. Fabric consolidates these capabilities into a single platform with shared storage, unified compute, consistent security, and integration experience. The goal should be to reduce architectural complexity, improve your time to insight, and simplify operations compared to managing multiple discrete services. Now, this doesn't mean Fabric is the right choice for every scenario. There are definitely trade offs here, which we'll discuss as we go deeper. But the fundamental value proposition is that about reducing the fragmentation and operational complexity that comes with integrating multiple different services. Now, let's talk about OneLake because this is really the foundation that everything else builds on top of. OneLake is Fabric's unified data lake. It provides a single storage layer for all analytics workloads in the platform. And when I say single storage layer, I mean that literally. Every workload in Fabric, whether it's Spark processing, SQL queries, KQL analytics, or Power BI reports, all of them read and write to the same storage foundation. OneLake is built on top of Azure Data Lake Storage Gen 2 under the hood, so you're getting that enterprise grade storage reliability, scalability, and performance that ADLS Gen 2 provides. But critically, OneLake stores data in open Delta Parquet format. This is important for two reasons. First, it ensures compatibility with a wide range of tools outside of Fabric. Second, it provides portability. Your data is not locked into a proprietary format. Every Fabric tenant gets one OneLake automatically provisioned when you start using Fabric. You don't have to set up storage accounts, configure access for them, or manage infrastructure. It's just right there. OneLake supports a hierarchical namespace, which means you can organize data in a way that matches your organizational structure. You do this through workspace and items, which we will talk about more later. But the key point here is that hierarchical organization enables you to apply security and governance policies at different levels, and those policies cascade down appropriately. The fact that all Fabric workloads use the same storage should eliminate data duplication. When you run a Spark job that writes a Delta table, your SQL warehouse can query the same table directly without copying the data. Your Power BI reports can visualize it, and then your KQL database can analyze it as well. All of that working on the same files in OneLake. Now let's talk about how OneLake organizes data architecturally. OneLake uses a hierarchical structure with 4 levels. At the top, you have tenant. Every organization using Fabric gets one tenant, and that tenant has one OneLake. Under the tenant, you have workspaces. Think of a workspaces as an organizational container. You might have a workspace for a finance team, another one for a marketing team, and then another one for a data engineering team. Each workspace is a security and collaboration boundary. Within workspaces, you have items. Items are the actual Fabric artifacts you create, like a lakehouse, a warehouse, a notebook, a pipeline. Each item type has a specific purpose. And then within items, you have your actual data stored in the Delta Lake format. So for example, inside a Lakehouse item, you'll have Delta tables, which are a collection of Parquet files with transaction logs. Now here's something important about performance. Data in OneLake is automatically optimized for query performance through conversion to vOrder format. vOrder is a proprietary optimization that Microsoft applies on top of Parquet. It improves compression and row ordering specifically for analytic workloads. This happens automatically in the background, so you don't have to configure it or manage it. All Fabric experiences read and write to OneLake using the same underlying storage. This is worth emphasizing because it's different from traditional architectures. In a typical setup, you might extract data from your lake into your warehouse and creating a copy. In Fabric, the warehouse and the lakehouse are both reading the same Delta files. There is no duplication, and this ensures consistency because there's only one version of the data, and it reduces storage costs significantly. Security and governance policies applied at the OneLake level cascade down to all data. So if you apply a sensitivity label at the workspace level, all the data in that workspace inherits that label. If you configure row level security on a table, that security applies whether someone accesses it through Spark, through SQL, or through Power BI. You configure it once and it applies everywhere. Now let's talk about shortcuts, which are a powerful feature for integrating external data without physically moving it. Shortcut enables virtual integration of external data sources into OneLake. So what does that mean? It means you can make external data appear as if it exists in your OneLake without actually copying it. You can create shortcuts to several types of external storage. First, Azure Data Lake Storage Gen 2, which is probably the most common scenario. AWS S3 if you have data in Amazon's cloud. Third, Google Cloud Storage for data in Google Cloud. And fourth, other Fabric workspaces, which enables data sharing between teams and organizations using Fabric. This virtual integration approach provides some significant benefits. First, it reduces the storage costs. If the data already exists somewhere, why pay to store it again and make another copy into your OneLake? Number two, it eliminates the data duplication, which reduces your operational complexity and removes the risk of having inconsistent versions. Number three, it enables federated data architectures where data can remain in the source systems still being accessible through Fabric for analytics. When you query against a shortcut, Fabric routes this query to external source transparently. From your perspective as a user, you're just querying a table in your lakehouse. But under the hood, Fabric is handling the authentication to the external source, translating that query to the appropriate protocol, fetching the data, and returning the results. All of this happens automatically. Now, there are performance considerations with shortcuts. If you're querying data over the internet from an external cloud, that's going to be slower than querying data in your OneLake locally. But for scenarios where the data is infrequently accessed or where the governance requirements demand that data stays in an origin location, shortcuts can be an excellent solution. Now, let's shift gears and talk about compute. Understanding Fabric's compute model is crucial for both performance and cost optimization. Fabric provides three compute engines, each optimized for different workloads patterns. Number one, you have Spark pools for big data processing. This is your engine for large-scale data transformations, ETL workloads, and data science tasks that need distributed processing. Second, you have the SQL Engine for warehousing and analytics. This handles your traditional SQL queries, dimensional modeling, and business intelligence workloads. Third, you have the KQL Engine for real-time analytics. KQL stands for Kusto Query Language, and this engine is optimized for time series data, log analytics, and scenarios where you need to query streamlined data with sub-second latency. Now, here's the key architectural decision that makes Fabric different. All three of these compute engines draw from the same shared Fabric capacity pool. You're not buying separate Spark clusters, separate SQL compute, and separate KQL clusters. You buy capacity in Fabric, and that capacity pool is shared across all workloads. Resource allocation happens on demand based on your workload requirements. When you run a Spark job, Fabric provisions compute resources for that job. When the job completes, those resources are released back to the pool and become available for other workloads. Same thing for SQL and KQL based scenarios. This on demand model should optimize resource utilization because you're not paying for idle dedicated compute sitting around just waiting for it to be used. Now let's go deeper on Spark compute specifically because Spark is often a significant part of data engineering workloads. Fabric provides serverless Spark compute that automatically scales based on workload requirements without manual cluster management. What does serverless mean in this context? It means you don't have to provision clusters, configure node sizes, and manage scaling policies or deal with cluster startup or shutdown. Fabric handles all of that infrastructure for you. When you run a notebook or a Spark job, here's what happens. Fabric provisions compute resources automatically based on the requirements of your job. Your code executes on all those resources. When the job completes, Fabric releases the resources back to the shared capacity pool. You're charged capacity units only for the actual compute time used. If your job runs for 10 minutes, you only pay for those 10 minutes. You're not paying for a cluster that's sit idle for let's say 24 or 23 hours a day. Spark pools in Fabric integrate with OneLake natively. This is important because it simplifies configuration significantly. You don't need to set up external metadata stores, configure connection strings, or manage credentials. Your Spark code just reads delta tables directly from OneLake with a simple path reference. The platform handles Spark version management, library dependencies, and runtime optimization. In traditional Spark deployments, you're managing Spark versions yourself, dealing with library conflicts, and tuning runtime configurations. Fabric takes care of much of the operational overload, though you still have control over configurations when you need it. Now, there are trade-offs here. With serverless Spark, you don't have the same level of control over infrastructure as you would with dedicated clusters. If you need specific instance types, custom network configurations, or a very specific tuning, serverless may have limitations. But for the majority of Spark workloads, the operational simplicity should still outweigh those constraints. Now let's talk about the configuration options you have with Spark in Fabric. Spark notebooks and jobs in Fabric support standard Spark APIs. That means PySpark, Scala, and Spark SQL all work as you would expect. If you're migrating existing Spark code, most of it should run with minimal changes. The APIs are standard Spark APIs, not proprietary variations. High concurrency mode enables multiple users to share Spark compute resources efficiently. In a traditional dedicated cluster model, if you have 10 data scientists, that might each get their own cluster, which can be pretty expensive. With high concurrency mode, those 10 data scientists can share the compute resources with automatic resource allocation and isolation between their workloads. Each user gets their own isolated session so that their work doesn't interfere with each other, but they are sharing the underlying compute resources. Environment configurations allow you to define custom libraries, Spark configurations, and runtime settings that apply consistently across notebooks and jobs. You can create an environment that includes specific Python packages, Spark properties, or system dependencies, and then attach that environment to multiple notebooks. This ensures consistency and makes it easy to update dependencies across your whole project by just updating the environment. Autoscaling adjusts executor count based on workload demands. You can configure minimum and maximum executors to balance performance and cost. During initial stages of a job where it's just reading and parsing data, you might only need a few executors. As the job progresses and gets into heavy transformations, Fabric can automatically scale up to more executors. Then, as the job winds down, it scales back down as well. This dynamic scaling should optimize your capacity consumption quite a bit. Now let's talk about the SQL Engine because this is where Fabric handles your traditional data warehousing and SQL analytics workloads. The SQL Engine in Fabric provides two deployment models, Warehouse and SQL Endpoint. These are not two separate engines. They are both using the same underlying SQL engine but with different capabilities. Warehouse provides full read-write operations. You can insert, update, and delete data. You can create stored procedures. You can manage transactions. This is a traditional data warehouse pattern where you're loading data, transforming it, and managing it through SQL operations. SQL Endpoint provides read-only analytical queries. A SQL endpoint automatically generates over every lakehouse you create. It gives you T-SQL access to delta tables in that lakehouse, but you can't modify the data through the SQL endpoint. It's for querying only. Both of these consume resources from the shared Fabric capacity pool on demand when queries execute. Neither of them requires you to provision dedicated compute. You're not sizing SQL pools or managing compute resources at all. When a query runs, it consumes the capacity units. When it completes, those resources are released. This on demand model is different from traditional SQL data warehouses where you typically provision a certain amount of compute and pay for it continuously. In Fabric, you're only consuming capacity when queries are actually running. Now let's clarify the distinction between the warehouse and SQL endpoint because sometimes it might cause confusion. Warehouse provides full read-write capabilities. You can insert data, update records, and delete rows. You can create store procedures and functions. You can manage transactions with commit and rollback. This is for traditional data warehousing patterns where you're managing mutable data. SQL endpoint automatically generates over every lakehouse. You don't create it manually. When you create a lakehouse, Fabric automatically provisions the SQL endpoint on top of it. This endpoint provides read-only T-SQL access to delta tables in that lakehouse. You can't modify data through the SQL endpoint, but you can run select queries with all the standard SQL capabilities like joins, aggregations, and window functions. Both consume capacity units from your shared Fabric capacity pool only when processing queries or operations. The billing model is the same. You're charged for the compute time used, whether it's in the warehouse or through the SQL endpoint. The primary distinction is read-write capability, not the compute model. It's not like one is provisioned and one is serverless. Both are using the same on-demand resource allocation from the capacity pool. The difference is functional. Warehouse lets you modify data and SQL endpoint is read-only. Now, when should you use each of the options? Use SQL endpoint when you're managing data through Spark or pipelines, or you just need SQL access for querying. Use Warehouse when you need full SQL-based data management, including updates and store procedures. Both can coexist in your architecture, and we'll talk about those patterns just in a bit. Now let's talk about the Lakehouse pattern, which is one of the core workload types in Fabric. The Lakehouse pattern combines data lake flexibility with data warehouse structure. So what does that mean? It means that you get the flexibility to store any type of data, structured or unstructured, in open formats like you would in a data lake, but you also get the structure and SQL analytic capabilities that you would expect from a data warehouse. Stored in open data format, Delta Lake provides asset transactions, schema enforcement, time travel, and all those enterprise data management capabilities, but is still open source and based on Parquet files. You are not locked into proprietary storage formats. The Lakehouse pattern enables SQL analytics and BI capabilities directly on the lake data. Traditionally, you would land data in your lake and then extract it into a warehouse for SQL analytics. With Lakehouse, you can run SQL queries directly on the delta tables in the lake. You're not duplicating data between the lake and the warehouse. The pattern should work well for organizations that want the flexibility of a data lake but also need to support SQL users and BI tools that expect structured data and relational semantics. Now let's get into specific of how Lakehouse actually works in Fabric. Lakehouse stores data as delta tables in one lake. Each delta table is a collection of Parquet files plus a transaction log that tracks all the changes. This supports both structured and unstructured data because you can have delta tables with strict schemas alongside raw files in other formats. Delta Lake provides ACID transactions, which means you get atomicity, consistency, isolation, and durability. Multiple users can read and write to the same table concurrently without corruption. You can also get time travel capabilities which let you query historical versions of your data or roll back to a previous state if needed. You can ingest data into a lakehouse through several mechanisms. Pipelines can copy data from external sources, data flows can transform and load data using Power Query, Spark notebooks can process and write data programmatically. All of these write delta tables to the OneLake. There's automatic table discovery and schema inference. When you write a delta table, Fabric automatically detects it and makes it available for querying. You don't have to manually register tables in Metastore or define schemas. Fabric infers the schema from the data and handles the metadata management. The SQL endpoint automatically generates over the lakehouse. As soon as you create a lakehouse, you get a SQL endpoint. This enables analysts to query the data using T-SQL without understanding Spark or needing to learn new tools. They can use familiar SQL syntax, and Fabric translates those queries to read from underlying Delta files. Power BI can connect to Lakehouse tables using Direct Lake mode. This is a special mode that provides near instant querying performance by reading the Delta files directly. It's not importing the data into Power BI's in-memory engine, and it's not using that query which hits the database for every visual transaction. It's reading the Parquet files directly from OneLake, which should give you the best of both worlds, fast performance and real-time data freshness. Now let's talk about the warehouse capabilities specifically because Warehouse provides enterprise data warehousing patterns on top of the Fabric platform. Warehouse supports complex queries, multi-table joins, aggregations, and analytical functions optimized for large-scale analytics. This is standard SQL data warehouse capability. You can write complicated queries with multiple CDEs, subqueries, window functions, and Fabric SQL Engine should handle these efficiently. Data modeling in Warehouse follows dimensional modeling patterns. You can create fact tables and dimension tables. You can implement star schemas or snowflake schemas depending on your requirements. This is standard data warehousing best practice, and Fabric's Warehouse supports these patterns natively. Warehouse supports T-SQL syntax including CDEs, Windows functions, and temporary tables, and stored procedures. Now I should mention that Fabric SQL is not 100% compatible with SQL Server. Some SQL Server's features may not be yet available in Fabric as well. Microsoft is continuously adding capabilities, but if you're migrating from SQL Server, you will want to test your T-SQL to ensure capability. Most standard SQL should work fine, but in the same time, some edge cases might need adaptation. Automatic statistics and query optimization occur transparently. In a traditional SQL Server or Azure Synapse environment, you would often manually create statistics or tune indexing. In Fabric, the engine learns from query patterns and creates statistics automatically. It optimizes query plans based on data distribution and query patterns. This reduces the tuning burden, though you can still manually create statistics if you need more control. Now let's shift to Data Factory, which handles the data integration in Microsoft Fabric. Data Factory in Fabric provides data integration capabilities through two main components: pipelines for orchestration and data flows Gen 2 for transformation. Pipelines handle workflow orchestration. This is where you're coordinating the data movement, triggering transformations, executing notebooks, integrating with the external systems, and managing dependencies between the tasks. Data Flows Gen 2 provides low-code data transformation through Power Query. Power Query is a transformation engine that's used in Excel and Power BI, so many analysts are already familiar with it. In Fabric, Data Flows lets you use the same familiar interface of building ETL transformations. Together, these should enable end-to-end data integration from extracting data from sources through transforming it to loading it into Lakehouse or warehouse destinations. Now let's get into more detail on the pipeline specifically. Pipelines enable workflow orchestration with a wide variety of activities. You can build data movement workflows with copy activities that move data from source to destination. You can trigger transformations by calling data flows. You can execute Spark notebooks for complex processing. You can integrate with external systems through REST APIs or even other connectors. The pipeline designer provides visual authoring with drag and drop activities. You're building workflows visually by dragging activities onto a canvas and connecting them. You can define parameters that make your pipelines reusable. You can use variables for runtime state management. And you have control flow capabilities including loops, conditions, and error handling. For example, you might have a for each loop that iterates over a list of files, processing each one, or an if condition that checks whether a file exists before trying to process it, or try catch error handling that routes through a different logic path depending on whether an activity succeeds or fails. Patterns and event based activation. Schedule triggers run pipelines on a time schedule like every day at 2 a.m. Tumbling window triggers handle backfill scenarios where you need to process historical windows of time. Event-based triggers fires when something happens, like a file arriving in a storage location. Pipeline activities can invoke many different operations. You can invoke Spark notebooks, passing parameters, and getting return values. You can call data flows to execute transformations. You can execute store procedures in a warehouse. You can even call external REST APIs to integrate the systems outside of Fabric. This flexibility should enable you to orchestrate complex workflows that span multiple systems and tools. Now let's talk about data flows, which handle data transformation in a low-code way. Data flows provide low-code data transformations using Power Query. Power Query is a data transformation engine that's been around for many years in Excel and Power BI. Many business analysts are already familiar with it, which makes data flows accessible to non-engineers. The Power Query interface supports hundreds of built-in transformations. You can filter rows, select columns, aggregate data, join tables, pivot and unpivot, split columns, and many other operations. There are also custom M functions for advanced scenarios where the built-in transformations are not sufficient. M is the language behind Power Query, and you can write custom M code when you need specialized logic. Data flows output to Lakehouse tables or warehouse tables. When you run a data flow, it reads from your sources, applies the transformations, and writes the results to delta tables in a lakehouse or to tables in a warehouse. There's automatic schema mapping, so if your source schema does not exactly match your destination, data flow can handle that. And there's incremental refresh capabilities to optimize data loading performance by only processing chained data rather than the full reload every time. Compute for data flows uses the shared fabric capacity. When a data flow runs, it consumes the capacity units from a capacity pool. The platform handles automatic scaling and resource allocation based on complexity of your transformations and the volume of data being processed. You're not managing compute resources, you are just running the data flow, and Fabric figures out how much compute you actually need. Now let's move into real-time intelligence, which brings streaming analytics and event-driven capabilities into Fabric. Real-time intelligence is designed for scenarios requiring some second latency and high throughput event processing. This is for use cases like IoT telemetry, application logs, kill stream analytics, financial trading data, or any other scenario when you're dealing with continuous stream of events and need to analyze them in real time. The real-time intelligence workload includes event streams for ingestion and routing, KQL database for storage and querying the time series of data, and real-time dashboards for visualization of live data. This workload should complement your batch processing patterns. While Lakehouse and Warehouse handle the historical analytics on data at rest, real-time intelligence handles streaming analytics on data in motion. Let me start with event streams, which handle the ingestion and routing of streaming data. Event streams provide event ingestion and routing capabilities. They can connect to sources like Azure Event Hubs, which is Azure's streaming platform. They can also connect to Kafka topics if you're using Kafka. They can connect to custom applications that push events to Fabric, and they support sample data for testing, which is useful when you're developing and want to test your logic without setting up real event sources. The visual designer enables defining transformations and routing logic. You can build event processing flows visually, similar to how you build pipelines. You can filter event based also on conditions. You can aggregate events over the time windows, and you can enrich the events by joining with reference data. All of this happens in the Visual Designer without writing any code. Supported destinations include several options. KQL Database is a primary destination for real-time analytics. Lakehouse is a good destination if you want to land the events for historical analysis. Warehouse works if you need the events in a SQL-based warehouse, or you can route to the custom endpoints for integration with external systems. Event streams handle the back pressure, retries, and handling automatically. If the downstream destinations are slow, event streams can buffer the events. If there are transient failures, it retries automatically. If event fails processed repeatedly, then it can route them to error handling logic. This reliability is crucial for production streaming scenarios where you can't afford to lose these events. Now let's talk about KQL Database, which is a storage and query engine for real-time analytics. KQL Database provides a time series optimized database using Gusto query language. Gusto is also known as Azure Data Explorer, which is Microsoft's time series database engine. It is designed specifically for high volume event ingestion and fast analytical queries over timestamp data. Ingestion is optimized for streaming scenarios with sub-second latency. From the moment an event arrives to when it's available for querying should be under a second. This enables near real-time analytics where you're seeing events as they happen. The throughput can handle millions of events per second depending on your configuration and capacity. KQL syntax provides powerful time series operations. You can aggregate data over time windows like count events per minute for the last hour, or you can also do pattern matching to find sequence of events. You have anomaly detection functions built into the language. They are forecasting functions for predicting future trends based on historical patterns. These time series operations are optimized and built into the query language, making them much easier than trying to implement the same logic in SQL. Data retention policies automatically manage data lifecycle. You can configure how long data should be kept. Old data can be automatically archived to cheaper storage or deleted entirely. You can have configurable hot and cold storage tiers. Hot storage keeps recent data in memory for instant queries. Cold storage keeps historical data on disk for cost-effective long-term retention. This automatic lifecycle management should optimize cost while ensuring the performance for recent data. Now let's talk about the real-time dashboards, which can visualize streaming data from KQL Database. Real-time dashboards visualize streaming data with automatic refresh. Unlike traditional BI dashboards that might refresh every few minutes or require manual refresh, real-time dashboards update continuously as new data arrives in the KQL database. This enables monitoring and operational analytics on live data. Dashboard tiles support various visualizations. Time series charts are pretty common for showing trends over time. Bar graphs work well for categorical comparisons. Pie charts can show proportional breakdowns. Tables are ideal for displaying detailed data, and all of these support drill through and cross filtering capabilities, so you can click on a data point to filter other visuals or navigate to more detailed views. These enable interactive filtering, so you can add parameters to your dashboard that let users adjust time ranges, filter by specific dimensions, or change other criteria. These parameters applies to all tiles on the dashboard, so users can dynamically explore the data without having to create multiple versions of the dashboards for different scenarios. Dashboards can be shared with the team members or embedded in applications. These are granular permission controls, so you can determine who can view the dashboard, who can edit it, and what level of access different users have. If you need to embed a dashboard in your own application, Fabric provides embedding capabilities with authentication and authorization handled through the Azure Active Directory. Now let's move to the data science capabilities, which enable machine learning workflows in Fabric. Data science experiences in Fabric include notebook authoring, experiment tracking, model training, and model registration through a unified interface. You're doing all of that within Fabric without needing to use separate machine learning platforms. Notebook supports Python, R, and Scala. Python is probably the most common language for data science, but if your team uses R or Scala, those are supported as well. The notebooks include built-in libraries for machine learning, scikit-learn for traditional ML algorithms, TensorFlow and PyTorch for deep learning, and many common data science packages are pre-installed. MLflow integration provides experiment tracking, model versioning, and model registry management. MLflow is an open source platform for managing the machine learning lifecycle. In Fabric, MLflow is integrated natively, so you can track experiments, compare model performance across the iterations, version your models, and register models in a central registry. Models are registered in MLflow for batch prediction within Fabric. Once you train a model and register it, you can use it for batch scoring on large datasets. This works well for scenarios like scoring all your customers overnight or predicting outcomes for historical data. For real time inference scenarios, when you need to score individual requests with low latency, integration with Azure machine learning or external endpoints is typically required. Fabric's data science capabilities focus more on training and batch scoring. If you need production grade real time serving with autoscaling, monitoring, and SLAs, you would typically deploy models to Azure Machine Learning or another serving platform. Now let's walk through the model training and deployment workflows in Fabric. Training workflows start by reading training data from OneLake. Your data is already in Lakehouse tables or warehouse tables, so you can access it directly from your notebook using standard Spark or Pandas operations. You train the models using Spark Compute. If you're working on large datasets, you can use Spark ML or distributed training frameworks. If your datasets are smaller, you can use single node libraries like Skeleton or TensorFlow running on the driver node. You track experiments through MLflow. As you run different experiments, trying different algorithms, hyperparameters, or feature engineering approaches, MLflow logs all of this automatically. You can see which experiment produced which metrics and compare experiments and understand what led to your best model. This creates reproducible and auditable ML pipelines. If someone asks you which model is in production and how it was trained, you can point to the MLflow experiment that shows exactly what data was used, what code was run, and what parameters were applied. After training, you register the model in MLflow's model registry. This gives model a name and a version. You can tag it with metadata like experimented, like which experiment it came from, who trained it, and what it's intended for. For deployment, batch scoring is a primary pattern within Fabric. You can create a notebook or a pipeline that loads the registered model, reads data to score from OneLake, applies the model, and writes the predictions back to the table. This works well for scenarios where you're scoring large batches of data on a schedule. For scenarios that need real-time inference, you would typically integrate with Azure Machine Learning. You can export your model from MLflow, deploy it to Azure ML's real-time endpoints, and then call those endpoints from your applications. This separation makes sense because real-time serving has different requirements around latency, scaling, and monitoring than batch training. Now let's talk about the capacity model, which is fundamental in understanding how Fabric billing and resource allocation works. Fabric uses capacity-based billing model. Instead of billing per query or per gigabyte of data processed, you purchase capacity units that provide compute resources shared across all workloads. Think of capacity as buying a pool of compute resources. You might buy 64 capacity units or 256 capacity units, depending on your needs. All of your Fabric workloads, pipelines, Spark jobs, SQL queries, KQL ingestion, everything draws from the shared pool. OneLake Storage is built separately on a pay-as-you-go basis. This follows the standard Azure Data Lake Storage Gen 2 pricing. You pay for the amount of data stored and any data transfer, but the compute for processing data is covered by your capacity units. This model should simplify cost management compared to scenarios where every service has a different billing model. You're buying capacity once and it covers all your compute needs across the platform. Capacity units actually work. So capacity is measured in capacity units, abbreviated as CU. Production SKUs start at F64, which provides 64 capacity units, and go up to F2048, which provides 2048 capacity units. There are even larger SKUs that go beyond that for enterprise workloads with very high scale requirements. There are also smaller SKUs, like for example F2 through F32, but these are available for trial and development purposes only. They are not recommended for production workloads because they have limitations in terms of performance and features. If you're building a production system, you should start at a F64 or higher. All Fabric workloads consume capacity from the shared compute pool. When a Spark job runs, it consumes capacity units. When SQL queries execute, they also consume capacity unit. When a pipelines orchestrate, they consume capacity unit as well. When data flows transform data, they consume capacity as well. And when KQL ingests events, that's also consuming the capacity. So to summarize, everything essentially draws from the same pool. Now, the platform monitors capacity utilization and may throttle operations when consumption exceeds the purchase capacity. Throttling ensures fair resource distribution across workloads. So if you're consuming more capacity than you purchase, the platform start delaying operations to keep you within your limits. This is why capacity sizing is important, which we'll discuss in just few slides. One thing to note is that background operations also consume capacity. Even during the parent idle periods, things like automatic table optimization, metadata operations, and system maintenance tasks consume capacity. So you won't have 100% of your capacity available for user workloads. There is always some overhead. Capacity sizing is one of those topics where there's no perfect formula. It depends on your specific workloads. Let me give you a framework for thinking about it. Capacity sizing depends on several factors. Number one is workload concurrency. How many users you are running queries simultaneously, how many Spark jobs are running at once. Higher concurrency requires more capacity. Second is data volumes. Processing 10 gigabytes is very different from processing 10 terabytes. Larger data volumes consume more capacity per operation. Third is transformation complexity. Simple select queries consume less capacity than complex or aggregations with multiple joins. Similarly, basic Spark transformations consume less than complex ML training workloads. Number four is required query performance. If you need sub-second query responses, you will need more capacity than if a few seconds is more acceptable. Performance and capacity are related. More capacity generally means faster execution. I recommend starting with smaller capacity for initial workloads and scaling up based on the observed utilization patterns. Don't try to perfectly size your capacity upfront. You can't know exactly what you need until you are running the real production workloads. Start conservatively, monitor your utilization, and scale up when you see consistent high utilization or throttling events. The Capacity Metrics app provides visibility into capacity consumption by workspace and operation type. This app is built into Fabric. It shows you which workspaces are consuming the most capacity, which types of operations are more expensive, and where you might have opportunities for optimization. Autoscale can automatically adjust capacity during peak usage and scale down during quiet periods. This is part of Fabric capacity features. If you have predictable patterns like heavy usage during business hours and low usage at night, Autoscale can increase capacity during the day and decrease it at night. This should optimize cost while maintaining the performance. Now, capacity can be paused when not in use. This is particularly useful for non-production environments or intermittent workloads. If you have a development environment that's only used during business hours, you can pause capacity at night and on weekends to stop the billing. When it's paused, you're not being charged, but you also can't run any workloads. Now let's talk about workspaces, which are a very important concept in Fabric. Workspaces organize Fabric items and control access. They serve as a primary security and collaboration boundary within the platform. When you think about how to structure a Fabric environment, workspaces are the main organizing principle. Each workspace maps to a folder in OneLake. All items in the workspace store their data in that folder. This provides a logical isolation and organizational structure. If you have a finance workspace and a marketing workspace, their data is physically separated in different folders in OneLake. Role-based access control at the workspace level grants the permissions. There are four roles: admin, member, contributor, and viewer. Admins can do everything, including manage workspace settings and permissions. Members can create and modify items. Contributor can create items, but they have more limited permissions. And viewers can only view items, they cannot create or modify them. Workspaces can be assigned to specific capacity. This is useful for cost allocation and performance isolation. You might have different teams or projects using separate capacity pools. For example, your finance team might have their own capacity and your marketing team has theirs. This allows you to track costs by team and ensure one team's heavy workload does not impact another team's performance. Alright, let's talk about Git integration, which brings the version control and DevOps practices to Fabric. Fabric workspaces support Git integration with Azure DevOps or GitHub. This enables version control, branching, and deployment automation for Fabric items. Think about how software development works. Developers don't edit production code directly, they work in branches, review changes through pull requests, and deploy through control pipelines. Git integration brings these same practices to analytics development in Fabric. You can connect a workspace now to a Git repository. Once connected, Fabric items in that workspace can be committed to Git. Changes are tracked, and you can also see who made what changes and when. You can roll back if needed, and you can also collaborate with your team through standard Git workflows. Now, let me describe a typical development lifecycle using Git integration. Git integration allows defining development, staging, and production workspaces connected to Git branches. This supports standard software development lifecycle practices. You might have a development workspace connected to a dev branch in Git. Developers will make changes in the dev workspace. When they are ready, they commit those changes to the dev branch. You have a staging workspace connected to a staging branch. Changes from dev can be merged into staging for testing. Stakeholders can review the changes in staging to validate that they work correctly. And then you have the production workspace connected to the main branch. Once the changes are validated in staging, they are merged to the main and deployed to production. Changes in the development workspace can be committed to Git, reviewed through pull requests, and deployed to production workspace through automated CI/CD pipelines. For example, you might have an Azure DevOps pipeline that automatically deploys to production whenever code is merged to the main branch. Fabric items including notebooks, pipelines, and semantic models are serialized to JSON and committed to Git. Everything is text-based files in Git, which means they can be diffed, reviewed, and version controlled just like code. This provides full traceability and rollback capabilities. This approach brings software engineering best practices to analytics development. It should improve the quality through code review. It also enables collaboration through branching and merging, and it improves the deployment reliability through automated testing and deployment pipelines. Now let's move into security and governance, which are very important for production deployments. Security in Fabric operates in multiple levels: tenant, capacity, workspace, and item. This provides a granular control over access and permissions. At the tenant level, administrators control who can use Fabric at all and what features are enabled. At the capacity level, you control which workspaces can use what capacity. At the workspace level, you control who has access to the workspace and what role they have. At the item level, you can configure even more specific permissions like who can view a particular report. Sensitivity labels from Microsoft Purview can be applied to Fabric items. Purview is Microsoft's data governance platform. If you're using Purview, you can classify data with labels like public, internal, confidential. When you apply these labels to Fabric items, the platform automatically enforces data classification and protection policies across the platform. For example, a confidential data set might not be downloadable or might only be accessible from corporate networks. So row-level security in semantic models and tables restrict the data visibility based on user identity. ILS ensures users only see data they are authorized to access. For example, sales managers might only see data for their own region. ILS is configured once in Fabric and it applies whether someone accesses the data through PowerBI, SQL, or any other interface. OneLake data is encrypted at rest and in transit using Microsoft Managed Keys by default. This provides baseline security without any configuration required. If you need additional control, there are options for customer managed keys where you manage the encryption keys yourself through Azure Key Vault. Now let's talk about network security options for connecting to Fabric securely. Fabric supports private endpoints for secure connectivity from on-premise networks or other Azure virtual networks. Private endpoints allow traffic to Fabric to flow over the private connections rather than the public internet. If you have on-premises data centers, you can connect to Fabric through VPN gateway or ExpressRoute. VPN gateway creates an encrypted tunnel over the internet. ExpressRoute provides a dedicated private connection that does not traverse the public internet at all, which some organizations will require for compliance and security reasons. Once you have connectivity established, you can use private endpoints to ensure traffic to Fabric stays on your private network. This means data does not get exposed to the public internet during the transfer. These network security capabilities should be enabled to you to meet compliance requirements that mandate private connectivity for sensitive data. Now let's talk about data lineage and discovery, which help you understand and manage how you should manage your data. Fabric provides automated data lineage showing how data flows between items. Lineage visualization maps out the relationships. Data comes from these source systems, gets transferred by these data flows, lands in these Lakehouse tables, get aggregated in these warehouse tables, and get visualized in this Power BI reports. This lineage helps with several things. Number one is understanding the data dependencies. If you need to make a change, lineage shows you what else might get impacted. Second is impact analysis. If you're going to modify a table, you can see which reports and downstream processes depend on it. Third, troubleshooting data quality issues. If a report shows incorrect data, you can trace back through the lineage to find where the problem originated. The data catalog indexes all Fabric items automatically. Every lakehouse, warehouse, notebook, pipeline, report, everything gets cataloged. This enables search and discovery across the organization. Users can search for, let's say, customer revenue and find all the relevant data sets reports, and documentation. You can enrich this with metadata tagging and classification to make the discovery even more powerful. Endorsement and certification workflows allow designating the trusted data sets and reports. You can mark certain items as promoted or certified. Promoted means the owner thinks it's ready for use. Certified means that it's been reviewed and approved by the organization's governance team. This helps users find authoritative data sources and avoid using duplicate or stale content. Now let's talk about the Power BI integration and how it plays a very important role in Microsoft Fabric. So Power BI is a visualization and business intelligence layer. Power BI is deeply integrated into Fabric. In fact, it's part of the Fabric now completely. When you create a Fabric workspace, you can create the Power BI reports in that workspace, and they have access to all the data in Lakehouse and Warehouse. Direct Lake mode in Power BI provides the fastest query performance. This is a new mode that's unique to Fabric. It reads in Delta Parquet files directly from OneLake without importing the data into Power BI's in-memory engine and without using direct query, which hits the database for every interaction. Direct Lake should combine the best aspects of both import and direct query modes, the performance of import with the data freshness of direct query. Semantic models in Fabric serve as a reusable business logic layer. A semantic model defines metrics, relationships, and calculations once. Then multiple reports can use the same semantic model, and this ensures that the consistency because everyone is using the same business logic, and it also reduces the duplication because you're not redefining the calculations in every report. Reports can combine data from multiple Fabric sources. A single Power BI report can include data from Lakehouse tables, warehouse tables, and KQL database all in one same visualization. This provides unified analytics across operational and analytical data without having to consolidate everything into a single data store first. Explain the direct lake mode in more detail because this is very important in Power BI. Traditionally, Power BI has two modes for connecting to data. Import mode copies data into Power BI's in-memory engine. This provides great performance because everything is in memory, but the data is stale. It's only as fresh as the last refresh. Direct query mode does not import data. Every time a user interacts with a visual, Power BI sends a query to the underlying database. This provides real-time data freshness, but performance can be slower because you're hitting the database constantly. Direct Lake eliminates this traditional trade-off between import mode's performance and direct query's freshness. It reads the Delta files directly from OneLake. The Delta Parquet files are highly optimized for analytical queries. Power BI reads these files directly without importing them and without sending queries to a database. This should give you both fast performance and data freshness. The key enabler here is the V-order optimization that Fabric applies to Delta files. V-order ensures that the Parquet files are structured in a way that's optimal for the Power BI to read. Combined with the fact that OneLake Storage is co-located with the Power BI compute, this enables very fast query performance. Direct Lake mode should be a preferred mode for Power BI reports and Fabric because it offers best performance and freshness characteristics. For organizations that have existing Azure Synapse analytic workloads, let me talk about migration strategies to Fabric. Organizations with existing Azure Synapse analytic workloads can migrate to Fabric following a phased approach to minimize disruption and validate functionality. You don't have to migrate everything at once. You can move workload by workload, testing and validating as you go. Synapse dedicated SQL pools can migrate to Fabric Warehouse. The pattern here would be to export your data and schema from the dedicated SQL pool, then import it to the Fabric using pipelines or SQL copy statements. Most T-SQL should be compatible, but you will want to test to ensure that any stored procedures or complex SQL works in Fabric SQL Engine. Synapse Spark notebooks are generally compatible with Fabric with minimal changes. The primary changes would be to update the connection strings to read from OneLake instead of the external storage accounts. The Spark API is a standard, so most of its PySpark or Scala code should be able to run without any changes. Synapse pipelines can be recreated in Fabric Data Factory. Most activities have direct equivalents. Copy activities, network activities, storage procedure activities, all of these exist in both Synapse and Fabric. The configuration is similar. You will need to recreate the pipelines in Fabric, but the logic should transfer pretty straightforward. The migration should be done pretty carefully with thorough testing to ensure the functionality and performance meet the expectations in the new environment. So now let's talk about when to use what each component. So with all these options, it can be get pretty confusing to what's appropriate for each scenario. So let's talk a bit more about it. This decision tree here should start with the understanding your data workload type. Choose a warehouse for traditional data warehousing scenarios. If you're doing dimensional modeling with facts and dimensions, if you need complex SQL analytics with a lot of joins and aggregations, if you're building reports over structured historical data, a warehouse should be your choice. It's optimized for SQL analytics and provides full read-write capabilities. You should choose Lakehouse when you need flexibility for both structured and unstructured data. If you're doing Spark based processing, if you have ML workloads with data science notebooks, if you need to handle diverse data types and formats, Lakehouse should be your choice. It provides a data lake flexibility whilst still enabling the SQL analytics through the SQL endpoint. Choose KQL Database for real time event scenarios. If you're ingesting streaming data, if you need some second query latency, if you're working with time series data and need time series analytic functions, KQL database should be your choice. It's specifically optimized for these high velocity event processing patterns. Now let's go deeper on the lakehouse versus warehouse decision, specifically because this is a very common point of confusion sometimes. You should use lakehouse when you need flexibility for both structured and unstructured data, Spark based processing, and ML workloads with data science notebooks. Lakehouse is ideal when you have diverse data types, when transformation logic is pretty complex and better suited to code than SQL. And when you have to do data science requires programmatic access to the data. Warehouse is optimal when you need full SQL capabilities, including the updates, store procedures, and transaction support for mutable data warehousing patterns. Use the warehouse when your transformations are primarily SQL based, when you need to support a large number of business users who think in SQL, and when data modeling follows the traditional dimensional patterns. Lakehouse provides cost advantages for append heavy workloads with infrequent updates. If you're continuously appending your new data but rarely updating existing records, Lakehouse Delta Lake format handles this pretty efficiently. Warehouse excels at workloads requiring frequent data modifications when you're updating the records regularly based on changing business data. Both can coexist in the same architecture. A common pattern is to have Lakehouse serving as a raw and processed data layer where you land the data and do initial transformations. Then Warehouse provides a curated semantic layer for reporting where data is structured in dimensional models for business users. Now let's talk about the performance optimization strategies for your Fabric workloads. Number one is query performance. So query performance in Fabric depends on several factors. First, data organization. How your data is structured in delta tables affects your query performance pretty significantly. Second is file sizing. Very small files are pretty inefficient, and very large files are also pretty inefficient. There's a sweet spot typically in a range of 100 MB to 1 GB per file, depending on your access patterns. Third is the partitioning strategy. How you partition your table affects which data gets scanned for queries. Good partitioning can dramatically improve the performance. Fourth is the compute resource allocation. Larger capacity provides more compute resources, which should improve the performance for your compute intensive workloads. Delta tables benefit from optimize and vacuum operations, so optimize compacts the small files into large files, improving the scan efficiency. Over time, as you append the data, you accumulate many small files. Optimize consolidates them. Vacuum removes the old version of the files that are no longer needed because of time travel. Running these operations periodically should improve the query performance. Z ordering arranges the data within the files to optimize for common filter predicate. If you frequently query data filtered by customer ID and date, you can Z order on those columns. This means data with similar customer ID and date values get physically stored together in files, reducing the amount of data that needs to be scanned when you filter on those columns. Partition columns should align with the common query filters. If you always filter by date in your queries, partitioning by date makes sense. This enables the partitioning pruning where the query engine can skip entire partitions that don't match your filter. Typically, time-based partitioning is the most common, partitioning by year, month, or day depending on your data volumes and query patterns. Now let's talk about the cost optimization because while Fabric simplifies the billing, there are still strategies to optimize your spending. Monitor capability utilization through the capacity metrics app. This app shows you which operations are consuming the most capacity, which workspaces are the most expensive, and where you might have opportunities for optimization. If you see a particular Spark job is consuming, let's say, 50% of your capacity, that is a very strong candidate for optimization. Pause capacity when it's not in use for development and test environments. If you have non-production environments that are not being used at night or weekends, pausing them should save significant amount of money. When capacity is paused and you're not being charged, but you also can't run any workloads. So this really only makes sense for environments where downtime is acceptable. Use shortcuts to external data sources when full data ingestion is not required. If you have data that lives in, let's say, an external ADLS account and you don't need to transform it, just create a shortcut to it rather than copying it to OneLake. This reduces the storage cost and avoids the compute costs of the copying data. Optimize data formats by using Delta with appropriate compression. Delta Lake supports several compression codecs like Snappy and Z. Good compression can reduce the storage cost pretty significantly. Typical compression ratios might be 3 to 1 or 5 to 1 compared to uncompressed formats, which directly translates to storage cost savings. Additionally, review your data retention policies. Do you really need to keep 7 years of detailed transactional data online? Maybe you can archive older data at cheaper storage tiers or aggregate historical data to reduce volume while preserving the important trends. Now let's talk about monitoring and observability, which are pretty important for operating Fabric in production. Fabric provides built-in monitoring capabilities across workloads. You can monitor capacity utilization to understand if you're over or under provisioned. You can monitor query performance to identify slow queries that need optimization. You can monitor your pipeline execution to see which pipelines are failing or taking too long. And you can also monitor your data refresh status to ensure that your data is staying up to date. All of this monitoring is built into the platform, so you don't need to set up external monitoring tools through, though you can integrate with Azure Monitor if you want centralized logging across your entire Azure ecosystem. Now, the Capacity Metrics apps is a primary tool for understanding capacity consumption. The Capacity Metrics app shows capacity consumption over time broken down by workspace and operation. You can see a timeline of capacity usage. You can drill into specific time periods to see what was running when you had high utilization. You can break down consumption by workspace to understand which teams are using the most resources. Throttling indicators show that when workloads were delayed due to capacity constraints, if the app shows throttling events, that's a signal you might need to increase the capacity or optimize your workloads. Throttling means operations were delayed to keep you within your capacity limits. Utilization trends reveal usage patterns, so you might see that you have heavy usage during business hours and very low usage at night. This helps you understand whether autoscale or capacity pausing might be beneficial. Per operation cost within the app breakdown which types of activities consume the most capacity. You might see the Spark jobs consume, let's say, 60% of capacity, SQL queries consumes 30%, and pipelines consume 10%. This enables targeted optimization efforts. Let's say if Spark is the biggest consumer, focus on optimization efforts over there. Now, Query Insights provide execution plans, statistics, and performance metrics for SQL queries in Warehouse and SQL Endpoint. This is similar to SQL Server query plans. When a query runs, you can view this execution plan to see how the SQL engine executed it. You can see which operations were expensive, how many rows were processed at each step, and where time was spent. Long-running queries can be identified and optimized. If you see queries taking minutes when they should take seconds, Query Insights can help you understand why. Maybe there's a missing index, though Fabric doesn't have traditional indexes in the same sense that SQL Server does, or maybe the query logic can be refactored to reduce the amount of data being processed. Historical query performance data enables tracking query performance over time. You can see if a query that used to run in 5 seconds now taking 30 seconds. This might indicate data growth that requires optimization or a schema change that broke an optimization. Now let me summarize some best practices for working with Fabric in production. First, you should organize your workspaces by team, project, or functional area. This enables clear ownership, access control, and capacity allocation aligned with your organization structure. You should not be combining everything into one workspace. Structure your workspaces thoughtfully to reflect how your organization actually operates. Second, use OneLake Shortcuts liberally to reduce data duplication and storage costs. If data exists elsewhere and you don't need it doesn't need transformation, shortcut to it rather than actually copying it. This maintains a single source of truth and reduces the operational complexity. Third, implement the incremental loading patterns in pipelines and data flows. Process only change data rather than full reloads. This reduces processing time and capacity consumption significantly for larger data sets where only a small portion changes every day. Number four is that you should apply sensitivity labels for Microsoft Purview consistently across your Fabric items. This ensures data classification and protection policies are enforced automatically. Classify the data once, and the platform handles the enforcement. Number five is that you should be establishing naming conventions for your workspaces, items, and tables. As your Fabric environment grows, consistent naming improves discoverability and maintains organization. Decide on a naming scheme early and then enforce it. Before you go and deploy the Fabric to production, let's go over a checklist of things that you should have in place. Number one is security configuration. Sensitivity labels should be defined and applied. A role level security should be configured for datasets that need it. Workspace roles should be properly assigned. Network isolation should be set up if required by your compliance policies. Second is monitoring and alerting setup. The capacity metrics app should be configured to track your usage. You should have alerting for capacity threshold breaches. Data refresh failure notifications should be set up so that you know when the pipelines fail. Query performance degradation alerts help you catch the performance issues before they actually impact the users significantly. Third is backup and disaster recovery strategy. Git integration should be enabled for item versioning. You should have documented procedures for OneLake data retention and recovery. Understand what happens if you accidentally delete a workspace or there is a data corruption issue. Fourth is capacity planning. Size your capacity appropriately for expected workload. Plan for growth. Configure how to scale if your usage patterns are predictable and would benefit from it. Have a plan for handling usage spikes like end of quarter reporting cycles. Fifth is documentation. Maintain data dictionaries so users can understand what data means what. Document lineage diagrams showing how data flows through the system in the Fabric platform. And record the architecture decisions so that the future team members can understand why things are structured the way they are. So now let's wrap up with a summary of what we covered today. Microsoft Fabric unifies data integration, storage, compute, and analytics into a single SaaS platform. This should reduce the architecture complexity compared to stitching together multiple discrete services from different vendors. OneLake provides a storage foundation with open delta format. Shortcuts enable virtual integration of external data. Automatic optimization handles the performance tuning. And all Fabric workloads use the same storage layer. Multiple compute engines, including Spark, SQL, and KQL, support diverse workload patterns. Batch processing happens in Spark and SQL. Real-time analytics happens in KQL. All of this is powered by a shared capacity model for compute, simplifying the billing and resource management. The platform here integrates deeply with the PowerBI for visualization, Git for version control, and Microsoft Purview for governance. This brings analytics into the broader Microsoft ecosystem with enterprise security and governance capabilities. Fabric represents a significant architectural shift towards unified analytics platforms. There are trade-offs here. You can gain integration and operational simplicity, but you might have to sacrifice some flexibility compared to best-of-breed services. Organizations should evaluate these trade-offs for their specific requirements. Again, thank you for watching this deep dive into Microsoft Fabric. If you have any questions, let me know. Thank you and have a good day.